couple of ideas that are both a theme of this session as well as a theme of this new conference. So if you look at this session, we're talking about innovations. And when I was looking at this banner behind me, I was noticing that one of the themes of IHRP is the business platform of hair restoration. So there's an aspect that comes together when we talk about even something that might seem simple as a graft holding solution that offers, one, the considerations to innovation, but also where does that fit into the concept of the business platform as each of you as physicians might be approaching your practice. So again, my name is Mathew. I'm with BioLife Solutions. My disclosure is that I am the Senior Vice President and Chief Technology Officer at BioLife. And some of you may be aware, I'm actually the co-developer of hypothermosol. What I'm going to talk about today is about holding solutions as a whole, and talking about some of the evolution of the holding solutions, the innovations behind it, some of the science behind it, and what is used currently in various practices. So if you look at this citation back from 2010, this basically gives an introduction throughout the literature of hair transplant, the type of different holding solutions that people have used throughout the published literature. Even starting with something as human serum, but then really the bulk of it tends to be what we might consider these isotonic solutions, such as a saline, a lactated ringers, plasmolite, and then during the last 15 years or so, movement into designed biopreservation media such as hypothermosol. There was actually even some reports of using sterile water, and the notation that the authors had was, if you're going to do that, you're pretty much going to kill all of your grafts. So the reality is, when the aspect of a graft holding solution was introduced into the early stages of these procedures, the likelihood is that they were selected due to convenience. What was sitting around in a physician's office that could then be pulled and poured into a petri dish and, to keep the grafts moist. And not necessarily as an aspect of a designed preservation step or a stability step in your process. Another aspect tends to be that it's cheap, something like saline. So you're looking at these solutions, I have saline, sitting in the office, I'll just go and use it, okay, great, not necessarily thinking about it as you might go as far as risk management or how do I improve each step, as you might look at other steps in the process. So let's go through a few of these. If we start with normal saline, one of the things to think about is what is it used for in medical practices. These are, normal saline is for fluid and electrolyte replenishment. It's primarily used for intravenous administration under normothermic conditions. Under normothermic conditions, body conditions 37 degrees, which are not the conditions that you tend to have grafts or strips at when we are conducting procedures. Normal saline actually has no buffering capacity whatsoever, and it has no designed oncotic support for the tissues and the stresses that are undergone during these procedures. But it is pretty much the traditional graft storage solution that's used for ex vivo storage, and there are a number of reports that speak to some aspect of saline throughout the hair transplant literature. Some folks might use plasmolite. Plasmolite is also an isotonic solution. It was designed for IV administration under normothermic conditions when patients have lost blood or for fluids. It has a little bit of normothermic buffering, again, normothermic, not the conditions that would be used during a hair transplant procedure, and it has no designed oncotic support. Then you might use something such as lactated ringers. Lactated ringers is also an isotonic solution. It was designed also for intravenous administration, normothermic conditions, has a little bit of buffering capacity, and a little bit of oncotic support. So a current theme running through all of this is these are solutions that were designed for IV administration of them in a blood loss situation, nothing to do with what we consider a preservation step for cells, tissues, or organs. You might have seen that in some papers and some use models, people have looked at DMEM or Williams E. These are culture media They are isotonic in nature, and they're meant to grow cells at 37 degrees. So as lab researchers, and I'm a PhD, we might take cells and we might put them into these types of culture media and grow them in an incubator. And so they're designed for normothermic conditions, but they're not designed for oncotic support, and they're not designed for preservation or for what we might consider an ex vivo graft storage step. Then you start getting into solutions that are along the lines of organ preservation media. So University of Wisconsin solution, Viaspan, Celsior, Custodial, HDK, Marshall solution. These are all medias that have been looked at, discussed, or used in some hair studies along the years. Now, the way that these are designed is that as an organ solution, they might be targeting a specific organ or area, such as abdominal or thoracic. They tend to be what we call hyperosmotic, not isotonic. And this is what we would call intracellular-like, as opposed to an isotonic or extracellular-like type of composition. And these are designed specifically for hypothermic buffering. Now, that sets up a discussion about hypothermosol. Some of you may be aware of this, some of you maybe not. But hypothermosol is a solution that is designed specifically for preservation of multiple cell tissues and organs. It was introduced into the hair transplant lexicon in the 2003-2004 time period by Jerry Cooley, with the idea being that when you are taking these hair grafts out of the scalp and either holding them or implanting them elsewhere, it is almost a micro-organ type of model. And in this micro-organ type of model, what is then the logic to use something such as a saline, which is not actually designed for any of that buffering or preservation, as opposed to solutions and media that are designed specifically for preservation of cells, tissues, and organs. Now, specific to hypothermosol, in addition to its design, its composition for hypothermic buffering, there are also aspects to it to address free radical scavenging, as well as the inhibition of cell death, such as apoptosis and necrosis. Along the years, you have seen studies, Dr. Cooley's early studies that were looking at hypothermosol, and then some later studies where he was also looking at hypothermosol in combination with ATP, which I will speak to in a moment. But one thing I wanted to point out is in this experiment that Dr. Cooley had done, which is a stress model, 5 days at cold storage, so longer than the type of period that you might be working with, but a stress model that gives good information. In an isotonic saline sample set, 0% of those follicles were able to engraft. With hypothermosol, 44% of those grafts that were held at 5 days at 2 to 8 degrees were able to survive. So that gives an indication of the type of what we might consider the preservation capacity for hypothermosol as a designed preservation solution. More recently, you might have heard the introduction of liposomal ATP by Bill Ehringer as a design, and then also Jerry Cooley and Bill Parsley as some of the early adopters of using hypothermosol plus ATP. And again, this is ATP that is specifically packaged in a certain way. If you look on the internet or in some of these supplements, there are a few different sources of ATP. One of the important aspects is how does one actually deliver it into the system. The way that Bill Ehringer has designed this as a liposomal packaged ATP allows it to then be crossed over to the plasma membrane and absorbed by the cell, as opposed to if it's just ATP alone and then it's just sitting outside of the cell and it actually breaks down. The cell does not actually take that up and cannot actually metabolize that. So I mentioned this experiment that Jerry Cooley had done a few years ago, and I had mentioned the 44% after 5 days of cold storage in hypothermosol compared to 0% if it was saline. When it was hypothermosol plus ATP, 72% of the grafts survived and engrafted after that 5 days. And there was also a study by Michael Biener that was looking at the hypothermosol and ATP in comparison to the saline over various periods of time. That was presented at the IHRP conference in Alaska in 2011. Some have also looked at using PRP as part of a holding media type of aspect. And this is an interesting concept. There aren't a lot of studies on this. In the 2002 to 2004 time period, these authors here had seen no difference if there was use of PRP as a holding graft solution. UBEL in 2005, there was some data showing an increase. However, when you actually read the article, it does not actually specify whether PRP was in the graft storage media or applied as part of the wound healing. So, in my opinion, there's an aspect of this where, scientifically speaking, in theory, the PRP should not have any positive impact during a graft holding stage. What PRP is applying is growth factors. During this hypothermic preservation period of the ex vivo hold, the metabolism of the cells and the tissues are greatly diminished at those temperatures. Actually, for every 10 degrees reduction in temperature, there's a 50% reduction in metabolism. So when we are holding the grafts at approximately 4 degrees, there's only about a 5% metabolic rate for those cells. When you actually then try to add in something like growth factors, it's actually counterintuitive. It doesn't necessarily cause more metabolism. It can actually, in theory, cause more damage. However, what could happen is perhaps it is bathing the cells. It is acting as a carrier that when it's implanted back into the scalp, some of those growth factors are then being carried over. That is a possibility, which then speaks to then the concept of actually using it as a paste around the tissue part of the graft before it's implanted or on the scalp wound. And Dr. Cooley has described that in some of his talks, how he uses it as a paste. So if we dig a little further into this difference between isotonic media and what we call intracellular-like designed biopreservation media. These isotonic solutions, such as saline, plasmolite, lactate bringers, in the culture medias, these are generally poor preservation solutions when applied specifically at low temperatures. They often rely on either no buffering capacity or they utilize something like bicarbonate, which is what we utilize in our blood system, which makes sense if you're using normothermic or cell culture type of conditions. Bicarbonate actually has extremely poor pH buffering capacity at low temperatures. So it's virtually useless, or maybe only as a supplement, when we are using this graft storage ex vivo stage. It really also does not have what we call oncotic support, having large molecules that when the ATP membrane pumps are dysfunctional, allow balance then to be given to the cells and tissues to counteract the passive flow of ions that occurs, which can lead to swelling as well as cell damage. So that is really why an isotonic solution really one is never designed for preservation of cells, tissues, and organs. If anyone is familiar with organ preservation for human transplant, no one uses something like saline or plasmolite when they ship an organ from one location to another location. They would use a designed preservation media. So in that type of model, the saline aspect went away many, many decades ago. So part of the question then is in these microorgan type of environments that you are working with, again, what is the balance for the logic for using something like a saline or a plasmolite? Now, that doesn't mean obviously that you don't get adequate or good results in some patients, and we'll speak to that at the end. Obviously, you do see some results. So that speaks then to this aspect of design innovative preservation solutions. How are they designed differently? The composition, first of all, involves multiple components, not just one or two that might be in a saline or isotonic solution. They're designed to restrict the passive exchange of water and ions, specifically during that hypothermic exposure when the cell membrane pumps are inhibited. These are really the biophysical characteristics of why these solutions have been termed intracellular type. They're meant to balance the cells, the inside of the cell, during that period of time when the cell cannot balance themselves. So one of the things, the picture sometimes tells 1,000 words. So one of the concepts is, do we really know what the cells look like within the hair grafts when we are going through our different procedures? There are multiple cell types that are involved in this complex microorgan type of situation. And some of the ones that are of relevance are certainly keratinocytes, fibroblasts, and then stem cells. This is not specific to dermal papillary stem cells, but certainly there are groups that have worked with that. And these fluorescent microscopes represent cells that have been subjected to a designed intracellular-like innovative solutions such as hypothermosol, in comparison to isotonic solutions, cold storage this is 1 day for the keratinocytes, 3 days, 1 day down for the stem cells, and then fluorescently labeled. And you can see the marked difference between what it looks like when you use a designed preservation media as opposed to an isotonic media that has not been designed for preservation at all. So the question I always ask sometimes is, what do your patient cells look like? This is a brand new slide. This is courtesy of Dr. Cooley. He just gave this to me this past week when I told him I was coming to this conference. And one of the things he vocalized, which you can discuss or give feedback, is this trend that he has seen or others have seen and has been discussed about 2-day hair transplants or overnight procedures. And perhaps that's something of experience that folks in the room are aware of or might be interested in. And in this experiment that he had done and has done now for, I think, multiple patients, he has actually had overnight graft storage at 2 to 8 degrees of the grafts in hypothermosol plus ATP, which he uses as a standard in his process. And then this is 1 year afterwards, 2,800 grafts. He was not able to notice a difference, in his opinion, between the overnight storage in comparison to the shorter time periods during a standard procedure when using hypothermosol and ATP. And this, the feedback that he gave to me to pass along was that it seems to be that this is coming up in discussion, both in terms of mega sessions, as well as in terms of sometimes the scheduling of the patients. In regenerative medicine, we actually look at this in terms of when one goes into a procedure, what contingency plans they have, should the patient not be able to go through with the procedure. I'm not sure how often that comes up in a hair transplant procedure. In regenerative medicine, they might have a day scheduled for a cell transplant, for example. And if they're having any type of arrhythmia or anything like that, they have to put off usually the procedure unless it's going to be potentially detrimental to their life. I don't know if that happens in hair transplant procedures where they might either get sometimes an arrhythmia or they get very nervous or scared sometimes about the procedure, and maybe you have to put it off and everything. And what if that happens after you have already started pulling out some of the grafts? Do you have to throw them away or no? It is possible that you might be able to then increase the stability window that you might have using improved preservation media, that perhaps you can then keep it at 2 to 8 degrees for a few more hours or for a day when that patient has either been able to lower their stress level or come back the next day, for example, or God forbid even the physician has an emergency that they have to run out for and they can't visit, but then you don't have to throw the grafts out. You don't necessarily have to have it as a lost procedure, lost cost for your practice also. So as a scientific aspect, these do all come from a number of studies. I do have this as a reference, depending on what the arrangements are with the conference afterwards. If there's sharing of the presentations, I'm more than happy to have direct conversations with folks to share some of my slides. So let me segue a little bit into regenerative medicine, which is really where our experience comes from, and a little bit more has come up in the past in the hair transplant field, as well as coming up a little bit in the future. Many of you might be familiar with the technology from almost 10 years ago from Intercytex that then passed on to Adirans. Looking at the stem cells and actually doing injection of stem cells for the growth of new hair. Hair clone is a resuscitated venture around that from some of the folks who have been involved with Adirans and Intercytex. So these intracellular-like biopreservation media that I'm speaking to that are designed, innovative, for a very specific purpose around biopreservation, and specifically, such as hypothermosol. These are currently used, completely separate from hair transplant, in clinical applications from head to toe in over 200 customer clinical applications throughout the globe, throughout every regulatory sphere currently of note. From a research perspective, we actually have over 250 paper citations, posters, abstracts, etc., that cite our improved, innovative intracellular-like biopreservation media methods for these new types of cell therapies, tissue therapies that are being developed, and you might hear in the news for things such as cancer and being able to program the cells for attacking the cancer. Those are all the actual type of groups that we work with on a regular basis. So part of the question that I want to leave towards the end as a discussion point to think about is then, is design innovative preservation needed? There's a scientific aspect, a clinical aspect to this, and then there's a business aspect. Because the reality is, if we took a poll of all the hair transplant physicians around the world as to whether they use something like hypothermosol or whether they use something like saline, it would probably be much more that they use saline. Now, there's certainly much more today that use hypothermosol than 10 years ago, and those, some might be considered either the leading physicians, the ones who can afford it, the ones who might be willing to absorb the costs for those improved methods. So there's certainly multiple considerations. So what I want to ask you is almost an analogy. Imagine that you are the hair graft, and you are being pulled out of a nice warm environment, and then you are put into a chilled solution during this ex vivo cold storage period. And it's almost as if any of us were sitting in the winter outside in Minnesota. And if you are wearing a tank top or a t-shirt, that is pretty much the equivalent of an isotonic solution such as saline or Plasma-Life. For a brief period, if you were just going out your back door to walk your dog just to have them go and relieve themselves, you might feel like you can tolerate this. If you had to be locked out and you were stuck out in the cold for a period of time, you would probably not survive very well, kindly, or at least have some damage to your tissues if you only had a t-shirt or saline, which would be the equivalent of an isotonic media for your graft holding. However, if you had a coat on, something that was covering you up, something that had more layers, something that was buffering you, that is the equivalent of this intracellular-like approach using something like hypothermosol. Now you are more able to sustain this exposure to the cold. It may also make a difference between if you are 20 years old, you are very fit, you go outside, it's cold, you might be able to stand outside for a few minutes and not be too upset. You are a 55-year-old male who comes in and is not necessarily in the best health or the best shape, the best nutrition, possibly even diseased. How is that person tolerating, or that person's grasp, tolerating the stress and exposure to the cold in comparison to the healthiest of your patients? So it is not always about improving the top end of your outputs. It might actually be improving the bottom variability of some of your poorest responders of the patients that come in. So what I would offer is a consideration to what we would call risk management. So it's difficult to quantify or control the stresses that the patient brings, the variabilities that the patient brings into the procedure before they actually start the procedure. So there might be cumulative stresses that impact the quality of the transplant, and they are cumulative the same way they would be as any stresses would be cumulative to us throughout the day. So the best, healthiest patients may not be as sensitive, and you may see no difference between your saline and your hypothermosol. Perhaps, perhaps not. But is it worth improved graft storage to reduce the probability of unsatisfied patients, especially in this internet age, where all it takes is one negative feedback on a message board that comes up on a Google search, and next thing you know, that is the impression that is left of that physician on the internet. Nobody takes posts down, they only add to it. So is it worth, as well as is it worth the cost of repeat transplants, if that patient has to come back and you have to do the repeat transplant at no cost to make up for anything that might have happened during the first procedure, as well as the negative publicity. So the ex vivo holding solution is one of the foundational stress risk points that are in the process as what we call the workflow from the start to the finish, and therefore one of the foundational things that you might look to reduce the stresses as well as to improve your overall processes. This is my contact information. If anybody wants to email me, I am always welcome to discuss. I'll be around afterwards, and we certainly have a booth afterwards for more information. These are some of the many different groups that I interact with. in terms of where we look to support best practices and innovation around this topic of biopreservation. Most of them are clinical groups as well as societies and governmental organizations. And this is really the mission that I and our scientific team, as well as us as a company, look to in terms of for improving best practices, methods across the board and throughout the world. So with that, if there's time for any questions, happy to take any. If not, we can put them off to later if it's a time constraint.